Hello everyone, welcome back to my channel. So today I would like to discuss about the topic design and analysis of approximate photocompressors for multiplication. Okay, before understanding about this topic, we have to know some terms like what is compressor. So what is an approximate compressor? So what is the need for doing approximate computing? Okay, we have to know all these things before understanding about this topic. So let me tell you a compressor. What is a compressor? A compressor is a digital model circuit which is mostly used in multipliers to reduce the operands while adding the terms of positive brackets. So generally compressors are applied in multiplication process for two reasons mainly: to improve the speed, and other reason is to deduct the number of steps involved in producing results. That's why we are using compressors in multiplication process. So we have different kinds of compressors like 3-2 compressors, 4-2 compressors, 5-2 compressors, 6-3 compressors, etc. So, but in this particular topic, so we are mainly concentrate on the 4-2 compressors. Okay, why? Because 4-2 compressors are mainly are widely used in fast multipliers to accelerate the compression process. Fine. Introduction about the topic. Multiplier is one of the fundamental units in computer arithmetic blocks. So moreover, why we are preferring 4-2 compressors means they are widely employed in parallel multipliers to accelerate the compression process of partial products. So here the main agenda of this topic. So the main agenda of this topic is, so in this topic we are mainly designing 3 novel approximate 4-2 compressors. So we here in this topic we are designing 3 novel approximate 4-2 compressors, and also we designed one error correcting module. So after that these designed novel approximate 4-2 compressors are utilized in the 8-bit unsaid multipliers. Okay, so it's a main agenda for topic. And compared with the exact 4-2 compressors, the designed approximate compressors, that means we are designing 3 approximate compressor designs, which shows they have to reduce the area, power and delay. When compared to exact compressors, the designed compressors reduces area, power and delay. Okay, finally, the designed approximate multipliers are accessed in image multiplication to compute image quality metrics like PSNR and SSIM. So I would like to discuss all these terms in the upcoming. It's the main agenda. So initially we are designing 3 novel approximate 4-2 compressor designs, and also we designed error correcting module. So after that these 4-2 novel approximate 4-2 compressors are utilized in 8-bit unsigned multipliers. So after that the designed approximate 8-bit approximate multipliers are accessed in image multiplication. Okay, it's a main agenda of our topic. So what is the need for doing approximation? We are having the exact 4-2 compressor already available. So why we need approximate 4-2 compressor? Why? Because so approximate computing is a trend nowadays. Approximate computing, which relaxes full precision to achieve high performance or low power consumption, is widely used in error resilient applications such as multimedia and machine learning. So what is the problem with the approximate designs? So the problem with these approximate multipliers or approximate designs, we can say, approximate designs introduce errors. They can introduce errors, but even though they are introducing errors, but they give efficiency in terms of power, speed and area. And these approximate designs have wide variety of applications like multimedia applications, machine learning applications, etc. That's why nowadays we are preferring approximate designs, even though they give errors. Okay. It is the existing 4-2 compressor. It is the architecture, standard architecture for existing or conventional 4-2 compressor design. So these 4-2 compressor can be built from 2 cascaded 3-2 compressor circuits. Here the 3-2 compressor is also called full adder. So see, observe here, full adder is also called as a 3-2 compressor. So the cascading of 2 3 to compressor will give you 4 to compressor. Okay, so it has the inputs y1, y2, y3, y4 and cin, and outputs sum, carry and cout. So it is the existing conventional code to compressor, generally used in the multiplication process. Okay, so we are modifying this architecture somewhat. So what is the disadvantages with this existing photo compressor system is, so more power dissipation, and also, so if you observe the equations, so it is the sum equation x1 xr x2 xr x3 xr x4 xr cn. So sum equation, carry equation and cout, these are the output equations. So if you observe the output equations, so conventional compressors are XR circuits, and partial product reduction is a critical multiplier block. So it is a XR circuits. So XR gate tends to contribute high area and delay. So this is the disadvantages with the existing photo compressor. Okay, so it has 5 inputs and 3 outputs. So what is the disadvantage with the existing photo compressor? Why we have to prefer approximate design space? So these are the XR circuits. XR gas tends to contribute high area. So that's why we are modifying these photo compressor design like this. So it's a huge table for an existing photo compressor. So totally having 5 inputs now. 5 inputs means totally we are having 32 combinations. We can simply verify this truth table by using these equations. Like it's a sum equation and carry equation, and it's a cout equation we have to observe here clearly. So by observing these equations, we can draw this truth table. So these are the inputs and these are the outputs. Like okay, so it's a proposed approximate photo compressor design. So it is a exact design. We are modifying this design to like this. In this topic, I have designed 3 designs totally. Three designs I have designed for photo compressor. Proposed approximate photo compressor design. Totally, I have designed 3 designs. Okay, so for design 1, it's a design 2, and it's a design. So observe here, it's a proposed designs. So here cin. So observe here cin, cout and carry are cancelled in these designs. So we are having y1, y2, y3, y4 and sum. So cin, cout and carry are cancelled. Why I am cancelling means it is an approximate design. Approximate means inexact design. It is not an exact photo compressor. It is an inexact design. Okay, it's a first design. So I am modifying this design like this second design, and third design is one simple arcade. So these are the 3 designs I have proposed. Okay, so what is the advantage with the designs with these designs is they show to get substantial improvement in terms of area, power and delay. So it's an advantage. What is the disadvantage with these 3 designs is they introduce more and more errors. Even though they are introduced errors, so we can get a substantial improvement in terms of area, power and speed, and also these are used in high-end applications like multimedia applications, like machine learning applications, etc. So in those applications, we use these kinds of designs in high-end applications. So the errors are very minor. Okay, so these are the logical expressions for the proposed designs. So if you see the first design output expression, that is y1 y2 plus y1 plus y2, that means it is an OR operation. So end of y3 plus y4 plus y3 y4. So simple. So the design, so if you observe here the design photo compressor design is totally in terms of XR gates. So here if you see the design is simple AND OR gates. Okay, approximate compressor designs are designed using simple AND OR logic circuits. Okay, it consumes very less power when compared to existing designs. So these are the 3 design output equations you can observe. So we are also designed one error correcting module. So what is the use of designing error correcting module is? So error correcting module is used to improve the accuracy of compressed output. So initially I had said, now if you use approximate designs, it leads to errors. So in order to improve the accuracy of compressed output, in order to improve the accuracy of compressed output, we are using error correcting module. Okay, so we are using error correcting module. So error correcting module is responsible for detecting and correcting errors that occur due to approximate nature of compressor. So it is an error correcting module. So the output equation of error correcting module. So that means error correcting module design is just similar to this kind of design. So the output expression is y1 y1 plus y2. That means OR operation of y1 and y2, and y3 plus y2. So it's a simple. Here we are having two OR gates and one AND gate. So output expression is simply so y1 y2 OR operation, and end operation of end of y3 y2. So simply two OR gates and one AND gate. So it's output equation. So let's observe the truth table of implemented approximate compressor. So we are having designed three designs: design 1, design 2, and design 3. So these are the inputs. So all these are the inputs: y1, y2, y3, y4. y1, y2, y3, y4. So the design 1 has an output, that is sum. So the design 2 has an output sum. So the design 3 has also an output sum. Okay. So design 1 inputs are y1, y2, y3, y4. Design 2 inputs also y1, y2, y3, y4. Design 3 inputs we can consider only y2, y4, y2 and y4. Okay, so these are the logical expressions for this proposed approximate photo compressors. Okay, so here we have, if you can observe, so you can get a minus in all these. So ED means error distance. So if you observe, so initially I had said, now if you employ inexact designs, that means approximate designs, we can get errors. So all these are the errors. All these are the errors. So why we are getting these many errors means, so these are not exact designs. All these are the inexact designs. That's why we are getting these many errors. Okay. So it's a design 1 errors, design 2 errors, and design 3 errors. So here also mentioned the probability. So here the probability of getting the probability of getting 0 is 3 by 4. The probability of getting 1 is 1 by 4. How we are getting 81 by 256 means, so initially we have to know, by assuming uniform distribution of multipliers input, the probability of product to be 0 is 3 by 4 and probability of product to be 1 is 1 by 4. So here the partial product, so if you see 0, 0, 0, 0, that means 3 by 4 into 3 by 4 into 3 by 4 into 3 by 4. That's why we can get 81 by 2. It's like that. So if you see this 9 by 256, here the inputs are 0, 1, 1, 0. Probability of getting 0 is 3 by 4. Probability of getting 1 is 1 by 4. Probability of getting 1 is 1 by 4. Probability of getting 3 is 0 is 3 by 4. If you multiply, we can get 9 by 2. Like that, we have calculated the probability for all these inputs. Okay. The probability of getting these partial product, that means 0, 0, 0 is 81 by 2. The probability of getting the partial product 1, 1, 1 is 1 by 256. Like that. So all these are the errors. So you can simply verify this truth table by using these logical expressions. Okay, if you substitute y1, y2, y3 values, we can simply get this column. Okay. Approximate 8-bit multipliers using approximate compressor. So initially we have designed 3 designs now. So after designing the 3 designs, we are using those designs in 8-bit unsigned multipliers. Okay, so we are proposing 4 different kinds of multipliers. like an 8-bit multiplier with design 1. Design 1 means this design. Multiplier with the design 1 and constant correcting bit. That means multiplier with first design and without error correcting module. What will happen? So second multiplier is 8-bit multiplier with design 1, but here we have error correcting module. So another kind of multiplier is multiplier with design 2 and error correcting module. So another kind of 8-bit multiplier is multiplier with the design 3 and error correcting module. Okay. So we are proposing 4 different kinds of multipliers. Okay, for the verification purpose. Okay. See here. So it is a proposed circuitry for 8-bit approximate multipliers. So totally it is here initially we are designing 8 by 8 unsigned multiplier. So 8 by 8 unsigned multiplier totally gives an output of 16 bits. Okay, 8 by 8. So here 8-bit as an multiplier, 8 bits as a multiplier. So another 8-bit as an multiplicand. So the output is 16 bits. Okay, so see here it is an 8-bit. So another 8-bit. So it is an approximation portion. We can say is an approximation portion. So it is a normal portion. We can say. Why I am calling this approximation portion means in this portion I am using the approximate designs. That's why I am calling this portion as approximate portion. So see here I am multiplying 2 8 bits. Okay, it's the first 8 bit and it is a multiplier. It's a multiplicand. Totally we can get the output, so 0 to 15. Totally we can get the 16 bit as an output. Okay, it is an output. Okay, so observe here we are employing error correcting module in approximation. So error correcting module is only used in approximation portion. So that's why the hardware overhead is also very small. So here the generally question arises. So we are additionally using error correcting module in the multiplier design. So it will also increase an area, right? So here no, I can say no. Why? Because error correcting module is only used in this particular portion, that means approximation portion. So that's why the hardware overhead is very small, I can say. So why we are using error correcting module? To improve the accuracy of the proposed designs. Okay. So we are employing only our design for approximate compressors in this portion. Okay, so the output of error correcting module is fed into the feed of adjacent photo compressor. So all these are the approximate photo compressor. So it is in full adder. So these are all exact photo compressors. So initially I had shown the architecture. So it is in full adder. So it is an exact photo compressor. So it is an half adder. It is an half adder. So if you keenly observe this kind of approximate multiplier architecture, proposed circuitry for 8-bit approximate multiplier. So just stage 1, stage 2, stage 3, stage 4. So in just 3 to 4 stages, we can get the output. We can get the 16-bit output. Okay, in just 4 stages, we can get the output. Just 3 to 4 stages, we can get the output. So see here, what is the benefit of using a compressor in multiplier architecture is? So see here 1, 2, 3, 4, 5, 6, 7, 8. Here the partial product height is 8. So it will reduce to, so initially here the partial product height, so we have to consider the highest 1, 2, 3, 4, 5, 6, 7, 8. Partial product in stage 1, partial product height is 8. So when come to stage 2, partial product height is reduced to, have to consider the highest 1, 2, 3, 4, reduced to 4. So in third stage, partial product height is reduced to just 2. In fourth stage, we can get the output that is reduced to 1. Okay, so it's a benefit of using compressors in the multiplier design. So if you see, within just 3 stages, we can get the output. Here, so every time the partial product height is reduced. First it is 8, after that we reduce it to 4, then 2, then 1. Okay, so it is the proposed circuitry for 8-bit multipliers. Okay, so we will see. So it is an 8 by 8 Dada tree multiplier architecture. So Dada tree multiplier architecture is it is one of the efficient multiplier we can say. So I can say this design is better than this Dada tree multiplier design. Why? Because here we are just following 1, 2, 3, 4 steps. But in Dada tree multiplier we are having 1, 2, 3, 4, 5 stages. Okay, so let me tell you. In 5 stages, we can get the output after 5 stages. So here the partial product. So in the other tree multiplier, the partial product height. So observe here, they have to consider the highest. In first stage, the stage 1. The partial product is stage 1. In stage 1, partial product height is 8. After that, it will reduce it to in stage 2, reduce it to 6. In stage 3, it reduces to 4. Okay, in stage 4, it reduced it to 3. In stage 5, it reduced it to 2. Okay, in 1, 2, 3, 4, 5 stages. So, Dada tree multiplier architecture requires 5 stages, whereas our proposed approximate multiplier will require only 3 steps to get the output, but the Dada tree multiplier architecture requires 5 stages. Okay, so here we have to see the comparison. So initially I said no. So the photo compressor, this photo compressor design is better when compared to these. And when compared to the conventional photo compressors, our designs are best, I can say. So practically you can see the example, the simulation result of photo compressor. I am not inserting any simulation output. So but here you can clearly observe the comparison. It is an exact photo compressor. It is the design 1 power consumption. It is the design 2 power consumption. It is the design 3 power consumption. So the design exact compressor design will require approximately 1.6 watts power, whereas our design, that is last design, that means this design is having only one OR gate now. So observe here, it will consume around 0.3 watts of power when compared to Excel. So that means there is a tremendous decrease in the power consumption if we use our approximate designs. That's why we are preferring approximate designs on compared to exact designs. Here I am showing only the power consumption. So area delay also gets reduced. Okay. So it is a multiplier 1 RTL schematic. So here I have proposed 4 kinds of multipliers now. So here 4 kinds of multipliers. Multiplier 1, 2, 3, 4. Multiplier 1 means design 1 with no ECM. That means there is no error correcting module. Multiplier 2, 3, 4. So let me show you the RTL schematics of those multipliers. So it is the RTL schematic of multiplier 1. So multiplier 1 means design 1. Multiplier 1 means approximate design 1. So multiplier 1 means our approximate design 1 and constant correcting bit and constant correcting bit 1. Constant correcting bit 1. So here there is no error correcting module. So the output of error correcting module is taken as the output of error correcting module is taken as logic. It's a definition of constant correcting bit. Here there is no error correcting module. Output of error correcting module is assumed as logic 1. Okay, so it's a multiplier 1 RTL schematic. So if you observe, here there is no RTL schematic. So it is the partial product generation block. So all these are the full adders and half adders. So it is a full adder. So it is a half adder. So all these are exact photo compressors. So it's a RTL schematic for this multiplier 1. It is a multiplier to RTL schematic. So when you observe this multiplier and this multiplier, here we are having error correcting module. So here we are having the error correcting module. So it is an error correcting module. So all these are the design ones. So all these are the design 1. It is a partial product generation block. So all these are the full adders. So it is an half adder. So all these are the exact photo compressors. Exact photo compressor. So it is an full adder. Exact photo compressor. Exact photo compressor like this. It is a simple RTL schematic for multiplier 2 architecture. So it is a multiplier 3. So what is the difference between the multiplier 2 and multiplier 3 means almost same. So only the difference is here, so it is an error correcting module. Here in multiplier 2 we are having first design. Here we are having design 2 architecture. Simple. It is a design 2 architecture. And multiplier 4 architecture. So it's a simple design 3. So all these are the design 3s. Design 3. So it is an error correcting module. The main difference is we are using design 3. That means simple OR gate. It's a partial product generation. So all these are the RTL schematics for various kinds of multipliers we proposed. So let me show you the power comparison of our proposed 8-bit multipliers. So we are it's our proposed circuitry for 8-bit approximate multiplier. So if you calculate the power for all these various flavors of multipliers, we can get the powers like this. It's a multiplier using exact compressor. If you design the 8-bit multiplier with only exact compressor, without any approximate compressors, we can get the power is like around 12.2 watts like that. So if you use approximate designs, the power is also observed here, and compared to the multiplier architecture with only exact 4-2 compressors, the power is somewhat reduced here. So see here, the power is tremendously reduced. Okay, so multiplier 4 means design 3 architecture and error correcting module. So the power is around 10.4 watts. Okay, power is reduced. Here I am showing the comparison for only power. We can also reduce the area. Can also reduce the delay. Okay, when compared to multiplier having only exact compressors. If you use approximate compressors, the power, area and delay have reduced. Okay, it's a main objective of our topic. Okay. Up to now we have seen what is an compressor. So how we are, what are the different kinds of compressors? How we are modifying the compressor architecture. So after that, how we are employing those modified architecture into 8x8 unsigned multiplier. Okay. So up to now we have seen up to this. So after designing 8x8 unsigned multipliers, approximate multipliers have several applications like image processing, image multiplication, image sharpening, machine learning applications, multimedia processing, high performance computing, cryptography applications, etc. So here I am considering one simple application, that is image multiplication application. So initially I had designed 8x8 unsigned multiplier now by using our designs, that means by using approximate compressor designs. So after that I am using these 8x8 multipliers in image multiplication, okay, to verify the accuracy of our design multiplier. So see here, image processing application. So here we are using a simple example, that is image multiplication. So it is an image multiplication application. Here we are how to see image multiplication application. So here we initially proposed 4 kinds of multipliers now: multiplier 1, multiplier 2, multiplier 3 and multiplier 4. After that, these 4 multipliers, 8-bit multipliers, are accessed in image multiplication process to verify accuracy of these multipliers. So what is a multiplier do? A multiplier is used to multiply 2 images on a pixel by pixel basis, thus blending the 2 images into single output image. Okay. So then each pixel value of one image is multiplied with corresponding pixel value of other image, thus combining of 2 images can be done. So after multiplication, we have to compute 2 parameters. The first one is PSNR and second one is SSIM. These PSNR and SSIM are called image quality metrics. These PSNR and SSIM, these 2 parameters are called image quality metrics. So let me tell you what is PSNR. PSNR means peak signal to noise ratio. PSNR value can be computed by comparing 2 images which are original image Another one is filtered image. Filtered image means noisy image. So always remember PSNR value must be high value. PSNR value must be high value. So high PSNR value indicates that the filtered image contains better image quality. It's a general theoretical formula for the PSNR. 20 into log 10 of maximum divided by ms, square root of ms, that means mean square error. Okay, whereas max is the difference between the value of two corresponding pixels, whereas mean square error is 1 by m. So it's a general formula. So here m and n are the dimensions of the image. Okay, m and n are the height and width of the image. So if you consider this kind of one image, the height is m and width is n. Okay, so I1 of m comma n. So I1 means is an original image without any noise. So here this I2 means filtered image. That means image which contains noise. So general theoretical formula for PSNR. Always remember PSNR value must be high value. So another image quality metric is SSI, Structural Similarity Index metric. SSIM is widely used in image quality assessment. So it is an metric that quantifies image quality degradation. That means how the image quality is degraded. So it will indicated by SSIM. Okay, always remember SSIM values is always range from 0 to 1. Okay, if SSIM value is equal to 1, that is structural similarity index metric value is equal to 1, we can say the two images are identical. Okay, see, a simulation process for getting these kind of image quality metrics. How we are getting after a multiplication of the image, how we get these two parameter values. So it's a process. So initially we have to take two images. Okay, two images, that is JPEG images or .png images. So after that, initially we have to take two images, any kind of images. Okay, any kind of images. That means the width and height of both the images should be equal. Okay, we have to take any images. So after that, those two images, that means two images can be converted to .x files. .x files. So why we have to convert .x files means the Verilog can't read the JPEG files. It can read only text files. What is an .x file? .x file means a .x file is a file format which is used to represent binary data in ASCII text format. So Verilog can't read JPEG images as an input. It can read only .x files. That's why there is an necessary to convert the .jpeg files to .x files. Okay, convert text images into .x files with the MATLAB code. By using MATLAB, we have to convert images into .x files. So here we are getting two .x file 1 and .x file 2. Here considering two images now, we have to get two .x files. So after getting two .x files, so these two .x files are applied to Verilog test bench. I have to write the code and we have to apply these two .x files to Verilog test bench. So after that, the output of multiplier. So after that, after applying these two .x files to Verilog, we can get another .x file as an output. Okay, another .x file as an output. So here I am using the software called Model Sim. Okay, by using Model Sim, so I am creating these .x files. After that, this .x file is again converted to image. That means JPEG file, JPEG format. What is the need for converting .x file to JPEG means to compute the parameters like PSNR and SSIM. Okay, .x file is converted into image and compute PSNR and SSIM values for each approximate and exact multipliers with MATLAB code by using MATLAB C1. So the simulation process gets solved. So it's a process we are using in the to get these quality metrics values. So here I am showing one sample output. So how the image multiplication can be done, how we are computing the parameters like that. So here, see, observe here. Here I am considering the two images. Any images you can consider. So here I am considering the two images of same height and width. After giving these two images, so initially I will convert these two JPEG images into .x files. After that, I am applying those two .x files to Verilog test bench. After that, I am getting another .x file. So again, I will convert two .x files into image like this. It is that means so the blending of two images can be done into a single output. So it is an image multiplication. The two images can be blended into a single output image like this. So it is the PSNR value for the first image. That is, it is the test image initially we have taken 44.13. So it is the PSNR value for another second image. So after multiplication, we can get for this image the PSNR value is 45.50 and SSIM value is 0.2. Initially I had said no, SSIM value always lies between 0 to 1. So here we are getting SSIM value is 0.2. So that's why. So initially what we have designed here, initially we have designed compressors. After that, approximate compressor. After that, I am using approximate compressors in multipliers. After multipliers, I am using one application like image multiplication to compute the parameters like PSNR, and so it is a PSNR value. It is 45.5, and it is a SSIM value. Okay, PSNR value must be as high as possible. Okay. So that's why image multiplication can be done over here. So what is the main advantage of doing this the approximate design is they have, so you can observe the area, power and delay gets reduced. So initially I have shown the comparison also for only power. So area and delay also gets reduced. Okay. So it's a confusion. So initially we have designed 3 approximate port to compressor design. After that, I had designed 4 approximate multiplier designs, multiplier 1, 2, 3, 4. So they will show area reduce significant decrease in power, area and delay. After that, after designing multipliers to validate the accuracy of the multipliers, I am using those multipliers in real life applications like the image multiplication application. There are n number of applications. I am considering only one application. You can try with these applications. Okay. Image multiplication application I am using here. After image multiplication can be done, I am also computed the parameters PSNR and SSIM. These are the image quality metrics. Okay, proposed approximate multipliers can also be designed using various feature scale technologies that are used in the current VLSI industry, such as nanomagnetic logic technology or quantum cellular dot automator technology, etc. So our work have extending toward implementing. So what is the future scope of our topic? What is the future scope? Future scope means this work can also be extended. Here I am considering only image multiplication. So this can be extended toward implementing multipliers in various other real-time applications like vision learning, high performance computing, IoT, cryptography, apart from image multiplication. It was performed and validated in this project. Okay, so we can consider these type of topic as our VLSI project idea. So here in this I am considering one image multiplication. Here you can extend this project by using another real life application like image processing application, image sharpening application, multimedia application. You can do by extending this. So we can get the significant reduced area power. So here I am proposing these kinds of designs. I am modifying the exact compressor to these type of designs. We can also, here I am using only radar logic test. We can also modify this design and try. So we can also get the area power delay can also be reduced. Okay, thank you.